You measure the force and you measure the deflection, then you will see that it will go like this. After some time, it will start to go like this, and after some time it will go like this, and after that time it will go like this and probably go here. And if at some point you stop applying the load and remove the load, it will go like that, and it will go like that, and if you start again, it will go like that and go like that. Right? This is called a typical force deformation curve of a structure, of a material, of a member, of everything. And I can promise you, most of you will be doing your research related to something of this kind. Right?
It only for flexor member?
It is for everything, but more clear in flexor members. But it is everything. Everything is like that. But sometimes we can see it, sometimes we cannot see it. But everything is like that. And that's where we come to build. So some action, some material may stop here, cannot go there. We call them brittle. So they have only some, they fail here. They don't have the rest of the curve. Then you can see here, this is initial stiffness. This is the only portion of the FD curve where your so-called modulus of elasticity may be a constant. May be a constant. That's all. Where it is in the beginning, initial. After that, it is not going to be. Here the stiffness is 0. Here the stiffness is negative. So stiffness can also be negative. Right? And here it is 0. And here it is changing, becoming nonlinear. And here this is called hysteretics. So this is energy consumed or contained in the structure. And that is the deformation. So every structure should follow this pattern if you test it. So those of you who are going to do this is with Dr. somebody, I don't want to name now, you will find testing, a lot of these testing in the lab, trying to find this curve. Some of you will be developing these curves through programming. Some of you will be using these curves to do some other analysis. But almost all of you who want to do something in structures somehow will be dealing with these curves in the future. So please look at this curve carefully. I cannot explain everything now. Step by step we will go there. Okay? FT curve. I want to give you another assignment next week which will be related to this curve. So please remind me that next Wednesday, after the first assignment is complete, I will give you a second assignment related to, please remind me. Slide number 80. Okay, so we will have an assignment on this curve. Let's skip that for now. Various stages of stiffness contribution. As I mentioned to you just now, stiffness is built up in various stages. Material stiffness, section stiffness, member stiffness, structure stiffness. And now you can see from here that stress strain curve looks like that. It is nonlinear, not constant. Curvature, moment curvature looks like that. Moment and curvature relationship not constant. One formula cannot define relationship between moment and curvature. That is the problem. One equation, stress equal to strain divided by E, cannot define this relationship. Rotation and moment cannot be defined by one relationship. And force and deformation cannot be defined by the formula that I showed you before, the spring constant, strip spring formula. So which means nothing can be calculated by a formula anymore, because nothing is constant. Everything is nonlinear. Nothing is linear. So again, whatever you learned, I'm sorry to say, wasn't that good so far, because you only deal with a very small part of this curve. Sorry, up to the Hooke's law. Yeah. Even that, anyway, so let's not talk about that for now. But you're right, up to Hooke's law. So we are now going where Hooke's law does not apply, which is everywhere, almost. Right? So please remember that we are going to be talking about that, these all stiffnesses. And in this course, we will talk about material stiffness, section stiffness, and a little bit about member stiffness. Structure stiffness next time. So these two courses are somehow related, my two courses. One more thing, last one, then we stop. Degrees of freedom, DOF. How many people know what is a DOF? Degree of freedom.
Free to move in particular.
Yes, freedom to move in one direction. Good. Same thing.
In terms of suppose they would resist.
Yeah, but same thing. So freedom to move, basically it's a freedom to move. So how many degrees of freedom are there in the universe? Hmm? Six? What do you think? Actually infinite. You can move in any direction. Nobody is going to stop you, right? There is no X and Y marked on in the universe or ground. Did you see anything outside saying X and this is Y, this is Z? No. So basically, things can move in any direction. It is our just way of looking at things X, Y, Z and 3 dimension. It's just our frame of reference. But basically, there is infinite ways in which particles can move. Right? In fact, there is only one at any given time. There is only one that we're looking at from one place of movement to another place of movement. One vector of movement, just one vector, and that vector can have components whichever way you like it, right? But yes, for our understanding and for our calculation and for our simplification, we have converted infinite degrees of freedom or a single degree of freedom, or however you look at it, into 7 degrees of freedom, not 6. We sometimes miss 7th degree of freedom, right? So this 7 degree of freedoms are axial deformation, shear deformation along one direction, shear deformation in other direction, torsional deformation, curvature in one direction, curvature in another direction, and warping. Warping is the 7th degree of freedom. How many people have heard about warping? Warping. What is warping? Sorry? I heard. So, deformation by torsion. Correct. It's like a distortion. Actually, it's not a deformation. So we have to make a distinction between deformation and distortion. Warping is a distortion, not a deformation. So you will say, what is the difference between distortion and deformation? There is a difference. So deformation due to torsion is actually twisting. But twisting produces warping. Warping is a distortion of the cross-section. Cross-section no longer remains plane, becomes out of plane, it becomes distorted. That distortion is called warping. Many times we do not study it, we sometimes ignore it, and sometimes we just don't know about it. Yes, please.
It is due to the torsion.
Yes.
So due to the torsion there will be shear stress.
Correct.
So but here it is axial stress.
Yes. Warping produces the distortion of the cross-section, which produces both shear and axial. Because the cross-section which is here is trying to come out of its plane. So it produces axial stresses also out of plane. Yes. Out of plane of the cross-section. So this is the plane of the cross-section. So this is the only which is going to be out of plane. So it is going to be twisting this cross-section out of plane, out of the plane of the cross-section. So it will produce also shearing and axial strength. So distortion and warping is quite important. Sometimes we ignore it for certain reasons, and we will talk next time. So let's stop here, I think. Slide number 83. How many more? Okay, I think this is the last one. So just to show you how on a cross section these 7 degrees of freedom are denoted. Oh, 7th is missing. Actually, I should go back. So that's the 6 that we will deal with. Warping is denoted by a triple head arrow. The rotation axial, forces by single head, moments by double head, and warping by triple head. And it has interesting units. Warping constant has units of inch raised to power 6. Not like inch raised to power 4 is the moment of inertia. Warping constant or warping properties, inch raised to power 6. Right? Very difficult to calculate the warping and torsional properties. We will come to that. But we will normally not consider warping in our design. Why? Because concrete structures have a very high warping stiffness, so we don't need to worry about that. That's why we will not talk about warping much. If I was teaching steel, then we will talk about warping a lot. But we will not talk about warping because concrete has very large stiffness and warping is negligible, can be ignored. And we can assume the cross sections to remain undistorted. That is the reason that we don't consider warping in our everyday discussion. But we will consider the effect of warping when we look at torsion. Okay, let's stop here. Any questions or anything not clear? I'm going to now summarize what we discussed. So you got an email from my office to go and get the apps? Yes. 4 p.m. Yeah, go in groups because we may not have space for all of you, but anyway, you can go. How many people have already gone to the office and seen the iLab and seen something?
I didn't enter, but I was informed of it.
Okay, it's okay, you can go there, it's no problem. So you can go and take a look at the iLab and also get your phones with the apps because we will do many of our assignments on the apps. Okay. Previous classes have never had this opportunity, so we'll see how it goes. How many people have Android phones? Android, okay, iPhones. Okay, difficult.